Hello, my name is Joel Chatfield, and this is the Physics Lab 1 presentation. The lab layout consists of 5 parts: intro, analysis of object motion, creating the computational model, the observed versus the predicted graph, and finally, a what if slash what does that mean. Main ideas. This is a lab dealing with constant velocity given by initial force, composing Newton's first law, with these being the central equations. The equation for finding final velocity, which is initial velocity, um, times the net force times change in time over mass. That in this equation, final velocity and initial velocity will end up being equal in our experiment because we're assuming the net force on the equation and system is going to be zero. And then we're going to find average velocity, multiply it by time, and then add the initial position in order to get our final position. So this diagram of key forces. So the initial forces acting upon it will be the ball's weight counteracted by the normal force, which will end up being net zero, and then that initial movement forward to give us initial velocity. And then while rolling, we are assuming that since air resistance is negligible and so is friction, it will be inherent. It'll be a net zero force because normal force and the weight plus gravitational force will be counteracting each other. So here is the analysis tracker video. I didn't have a ball, so I rolled a bottle of saline solution across it. You notice the desk is slightly slanted, which did affect the data a little bit, but it was the only free surface I had to do it. In this case, data distance, it started at a negative 5.709 and traveled until what was marked as 0 meter, but is a total of 74 centimeters. And then the size of the data was regulated such that a unit was considered a centimeter. So when creating the computational model, in the picture above, the top equation is the same as the first bullet point. The ball's velocity is equal to its previous velocity plus the net force divided by the ball's mass times the change in time, delta t. And then that equation will end up, the ball's velocity will never end up changing because F net is zero for the whole equation. And then the position is just its previous position plus the velocity times delta t. And in this case, delta t is 1 over 30 because the video operates at 30 frames per second. This is the entire equation. It ends up rolling for 0.9 seconds when I went back and checked through the video for the length. So while t is less than 0.9. As you can see, the net force is always considered zero. The ball is neither speeding up nor slowing down according to it. And then to the right is my link. Here's my charted data. As you can see, the tracker is initially slower than the ball, but actually ends up finishing faster. I believe this is because my desk was slanted slightly, something the model can't account for, but I think it affected it a little bit, which I'll get into more later. What does it mean? What happened if the axes were flipped? Nothing would really happen. The data would show it moving in a positive direction, but overall, how much movement is done and how much it's affected by axis flipping is effectively zero, because axes are an arbitrary decision of where zero is used only in terms of calculations, not in terms of defined force and movement. You move the same distance, it's just where your start and stop is. And is the net force of zero justifiable? No. As was shown with the tracker and all that, the desk was slightly slanted, so gravity did have an effect on it. And even if gravity hadn't had an effect on it, there was still the inherent issue of us ignoring friction and air resistance, which would exist in a real system, which was also likely a source of the deviations between the model and the actual math. which was shown at the beginning, where the model went slightly faster at the beginning as the initial force fought against friction to go. This has been my presentation.